SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome back. So, we have been looking at the von Neumann stability analysis in the last couple of classes, okay, and we found that for the diffusion problem, the scheme like FTCS is stable when alpha is less than half, basically the diffusion number is less than half, nu delta T by del x square is less than half. And for the convection problem, what we observed is that the explicit scheme, if you use the FTCS, it is unconditionally unstable. So, the central differentiation scheme with an explicit approach is unstable for the linear convection problem, okay, because the amplification factor is always greater than 1 regardless of what is the Courant number or the CFL number, that is C delta T by del x that we are using. Okay. On the other hand, when we use the implicit scheme, what the scheme told us is that it is unconditionally stable for the linear problem. Of course, when you try solving it for a nonlinear problem or a problem like Navier-Stokes equation, you will have some more practical consideration. First of all, the implicit scheme is not always preferable, especially when you are trying to solve a time accurate problem. Okay. And so, those considerations will come, but what von Neumann stability tells you that if you use an implicit scheme, it is unconditionally stable whether the problem is diffusion or the convection. Okay. Now, we will look at the FTBS scheme. Okay. So, this is our convection equation del U by del T plus C del U by del x is equal to 0, and if C is greater than 0, okay, what I have seen from our experience is that we use the FTBS scheme, okay, forward in time and backward in space, then it is stable for C delta T by del x less than 1. So, this we have seen from our experience, right, and similarly if C is less than 0, okay, then we have to use this FTFS, okay, forward in time and forward in step. I mean, this is just to honor the speed of sound. So, if it is C is greater than 0, then we have what you have to do, the grid points that you select is I minus 1 and I to calculate the gradient, okay, because the wave is going in the right direction. When the C is less than 0, then you select I and I plus 1 and to calculate your gradient del U by del x, because the wave is going in the left direction. Okay. So, both these cases are called upwinding, okay, upwind scheme, okay. Because it is one sided, we are not using the central differentiation and we are using the information from the wave to basically find your gradient, okay. So, we will use the von Neumann stability analysis and see for C greater than 0 if our whatever observations we had that it is stable for C delta T by del x less than 1 is basically valid or not, okay, and we find out from the von Neumann stability analysis. Okay, so, let us write the discretized form. This is U I n plus 1 minus U I n by delta T plus C U I plus 1 n minus U I minus 1 n. Sorry, what I am using is the first FTBS, right. So, this will be U I n minus U I minus 1 n by delta x is equal to 0, right. So, use this, rearrange it, U I n plus 1 will become U I n minus C delta T by del x, okay, which we denote by lambda, okay, and then it will be U I n minus U I minus 1 n equal to 0, okay. So, just rewrite this as lambda not equal to 0. We have already put it on the right hand side. Okay. We use our expression u y n will be g to the power n e to the power I and phi. Okay, and u I plus 1 n similarly e to the power n e to the power I plus 1 I phi, and u I n plus 1 for example g to the power n e to the power I phi. So, basically we have this separation of variables. When we are trying to solve the differential equation, we have basically separated our time and the space. Okay. Put these things here. Okay, what we will get is this is g to the power n plus 1 will be equal to g to the power n. I am taking this e to the power I phi common everywhere, minus lambda, this is 1 minus e to the power minus I phi, right. You can rearrange it. This is the g to the power n is here also, g to the power n 1 minus lambda 1 minus cos phi, and then minus minus will become plus I sin phi, right. So, that will, so now write the amplification factor g to the power n plus 1 by g to the power n. Okay. So, that you can do 1 minus lambda, okay, and plus lambda cos phi and minus lambda I sin phi. Okay, just rearrange it. So, 1 minus lambda plus lambda cos phi, okay, that is one part, minus I lambda sin phi. Okay. So, this is the value of g. Okay. Now, it is again a complex expression. Okay. So, you have this real part of g and then you have imaginary part of g. Okay. And we want to find out for what condition of lambda it will be stable or whether it is stable or not. Okay. That is our task. Okay. So, what we will do, we will use you might have used the complex plots, okay, in your undergraduate course, okay, or in any math course. So, let us say if you have so let us say you have e to the power I phi, so that is cos phi plus I sin phi, and you can represent it in a complex plane. Okay. So, you can have this real plane. Okay. Let us say this is my g. So, this is my real g and this is imaginary g. Okay. So, this has got a radius of equal to 1, okay, and phi will go all the way from 0 to 2 pi. So, you can basically, this is a circle, not made a very good circle. Okay. Just okay. So, something like this. So, my radius is equal to 1. So, this is a representation of e to the power I phi, okay, or is equivalently cos phi plus I sin phi. Okay. So, if you have let us say e to the power 2 I phi, okay. So, accordingly you can have this 2 e to the power I phi. So, it will have radius of 2, right. So, basically r cos theta and r sin theta, these are the two terms. Okay. So, now let us look at what term you have. So, g is equal to 1 minus lambda plus lambda cos phi minus I lambda sin phi. Okay. So, we will use the complex plane. So, these kind of plots are called Argand diagram. Okay. So, what we will do, we will take first lambda equal to 1. Okay. If you take lambda equal to 1, this will become g, this will become, this term will become 0, this will be cos phi minus I sin phi. right. So, even if it is minus, you will if you plot from 0 to 2 pi, you will have the same thing. Okay. Let me just plot it. Okay. So, the radius is equal to 1. Okay. So, let us say this is my 0.5, this is 1, this is 0.5, this is 1, this is 0.5, this is 1, this is 0.5 and this is 1. Okay. So, equal to cos phi plus I sin phi. So, we will have a plot which will connect this origin is at 0, right, and it will go like this and connect like this. Okay. So, this is a circle, okay, whose radius is equal to 1, and you can see that its amplitude is 1 everywhere, right. So, if you take the amplitude of g, so this g bar is equal to 1, okay, because this is our amplitude, you can take it anywhere, this will be equal to 1. Okay. Now, let us take lambda equal to 1 by 2. Okay. So, then g will become 1 by 2 plus 1 by 2 cos phi and then minus I 1 by 2 sin phi. Okay. Now, here you can see that real axis has shifted by 1 by 2, right. So, this is where our origin will be. Okay. Let me use some other color, maybe I will use this color. Okay. And the radius is 1 by 2, right. So, it will have another circle, okay, which will go like this, it will be like this, right. So, this is going 0.5 and you can see that you can take the amplitude anywhere. Okay, the radius is 0.5, but if you take the amplitude anywhere, okay, so that will be less than 1. So, this is the maximum amplitude is this which is g is equal to 1, all other places it is less than 1, right. So, this is basically stable. So, 1 is also stable because there is g is just exactly equal to 1. If you take 0.5, then also it will be stable. You can take different values of lambda, let us say 0.75, okay, or whatever values you want, and see that it will always be inside this circle, one circle, unit circle, and it will always the magnitude will be always less than equal to 1. Okay. So, all these are basically g less than 1. Okay. Now, let us go to lambda equal to greater than 1. Okay. Let us take lambda equal to 3 by 2. Okay. So, if you take lambda equal to 3 by 2, then g will become minus 1 by 2 and plus 3 by 2 cos half minus I 3 by 2 sin half. Okay. So, the origin for this plot also circle, the origin will be minus 1 by 2 and 0, right. So, that is basically if I can use another color, maybe this one, this is my origin, I fixed the origin and the radius is basically 3 by 2, right. So, now I have to start make a circle from here and it should go to 3 by 2 on either side. So, this is 3 by 2, okay, this is fine, minus 0.5 plus 1 3 by 2, here also this is 0.5 and it has to go to minus 2 here. Okay. So, that will be 1 minus 1.5, okay, and this is my minus 2, okay, this is minus 0.5 minus 1 minus 2. Okay. So, let us make a circle fixing the origin here and use the color that we are using. Okay. So, it has to go on either side 1.5. So, this is my 1.5 and somewhere here my 1.5. So, connect it like this. Okay. Okay. So, this is my circle that will be getting. You can easily write a simple MATLAB code and plot this, okay, and you can see that uh, the amplitude of this is always greater than equal to 1, right. It will always be greater than 1, okay. So, this is basically this is uh, okay, from here we will connect. So, this is 1 and here it is greater than 1, here greater than 1, everywhere you will see this is basically greater than 1, okay. So, in this case the G is always greater than 1, right. So, you see that as you increase the value of lambda greater than 1, it goes into the zone where your amplitude factor is always greater than 1, okay. And this is precisely the reason why we find that when we use this value of lambda equal to C delta T by del x greater than 1, your scheme becomes unstable because your amplification factor becomes greater than 1, okay. That means any wave if you have lambda greater than 1 is going to basically this amplitude will increase in time and finally it will become unstable, right. So, this FTBS, okay, let me write it here. FTBS for convection scheme is conditionally stable with lambda equal to C delta T by dx less than equal to 1, okay. So, this is what we have observed earlier also while trying to basically solve it numerically the convection equation, that when the lambda was greater than 1, it was you would start seeing wiggles initially and it will quickly basically become unstable, it will explode, okay. So, this we observed. I will just show you what we have done through this plot, okay. So, this is what I was trying to show you, okay. So, this is lambda equal to 0.5, okay, and you can take this amplitude anywhere, okay. This will be less than 1, this is lambda equal to 1, okay, and it will be 1 everywhere, and then we have lambda equal to 1.5, okay. If you can use this color, okay, this is greater than 1, okay, and because of that it becomes unstable. So, you can when you go back, please work it out and see a plot for different lambdas and find out when it becomes stable and when it becomes unstable, okay. So, similarly you can try this this von Neumann stability analysis for many different problems, okay, and I will not go through all of these, but I would basically request you or basically ask you to try this as a practice assignment, okay. So, you can take different schemes that we have discussed in the class. So, you have this CTCS scheme, leapfrog scheme, okay. So, which is like the central differencing in space as well as central differencing in time. So, both has got a central differencing space and time, and see whether this scheme is stable or not, okay, using the von Neumann stability analysis. Similarly, look for the Lex-Frederick scheme which is basically FTCS, but now we have a the UI term is taken as the half of the I plus 1 and I minus 1, okay, and then you have the Lax-Van Dort scheme which has additional diffusion on the central diffusion scheme. So, use your Fourier Ansatz, okay, u equal to ui n is equal to e to the power n e to the power I phi, and see what stability characteristic you find for these equations. Are there any conditions where it becomes stable, and try it for convection problem, okay. This is for convection problem. Similarly, you can try. So, this we have already tried implicit FTCS, we have already done that, okay. Try for the Crank-Nicolson also, we have discussed the Crank-Nicolson scheme also, and find out the stability conditions for all these schemes, okay. So, this is the homework for you, and we will continue discussing it as and when necessary, but this is something we should be very basically you should be convenient with the stability conditions. Okay, it should not be appearing that you are using the central differentiation scheme without knowledge to a convection problem. Okay, so if it gets ingrained, basically CFD knowledge that if the lambda or alpha, what are the conditions when it can be stable, when it cannot be stable, what are the schemes which are stable or not stable, it will become very useful for you, okay, while choosing your scheme for a particular problem. Okay. So, what I will do in the next class, so we have done the stability analysis, now we have to go for something called error analysis. Okay. So, what is error analysis? So, right now we have only talked about whether the scheme is stable or not, and from the lax equivalence from you we know that if the scheme is consistent and stable, the convergence is guaranteed. But even if it is converged, okay, depending on what scheme you are using, you will have basically certain error. Okay. So, the errors can be of two types. Okay. One is the dissipation error, okay, and other is dispersion error. Okay. It is also sometimes called diffusion error, although there are some differences between the dissipation and diffusion, okay, but they are both related to similar terms. Okay. So, we will be alternatively using the dissipation error or the dispersion error. The dispersion error is also called the phase error, okay, and this can also be called an amplitude error. Okay. So, we will look at these two errors because that will tell us the information about which method is more accurate. Okay. We have already discussed about the order of accuracy earlier. Okay. So, the dissipation error will basically we can figure out from our order of accuracy. So, this is basically order, okay, and this dispersion error, which is also very important if you are particularly interested in basically high fidelity flows. Okay. So, we will discuss what is the dispersion error. So, this is related to the resolution of the scheme. Okay. So, dissipation error is related to the order of the scheme and dispersion error is the related to the resolution of the scheme. So, what does it mean? So, dissipation error. So, let us say you are trying to solve a problem which is like this, okay, and if the scheme has got dissipation error. So, what will happen with time, okay, as you solve it. So, let us say you are trying to use your convection equation, okay, plus C del E by del x equal to 0. Okay. So, it should basically ideally just propagate like this, okay, and then go like this, okay, with the speed which is c. Okay. But what happens actually is that it propagates, but also you will see that the magnitude comes like this. Even it can with time it can even go lower. Okay. So, for example, it is going like this. Okay. We have already seen that, right, and further if you go down, then it will probably go like this. Okay. So, you can see that the amplitude is started going down. So, what started with this big amplitude, now it has become like this. Okay. So, if there is a change in the amplitude, okay, particular decay of the amplitude, that is called the dissipation error. Okay. So, this is our dissipation error. Okay. Now, what is dispersion error? Okay. Let us look at the same wave and we are trying to solve it using let us say the central differentiation scheme. Okay. So, this let us say we are solving FTBS scheme. Okay. Now, let us say we are trying to solve this using FTCS scheme, okay, central differentiation, which we know that it is unstable, right. So, the exact solution will be something like this. Okay. okay. But you will see that if you are using a central differentiating scheme, okay, so you will start seeing wiggles like this. Okay, the amplitude may not go down much, but you will have wiggles, let us say here and here. You may have wiggles here also or here also. Okay, similarly, you may start seeing wiggles at the discontinuous region. Okay, and ultimately what will happen if you continue running it, then it will blow up. Okay, the scheme will blow up. Okay, so what you are seeing here in this compared to the dissipation error. So, in the dissipation error, it is propagating, but it is basically the magnitude is going down, okay, or maybe it is smearing out. Okay, but in this case, the amplitude or magnitude is not going down, but you start seeing some oscillations here, okay, like here. Okay, so what is exactly happening is that, let us say, we have discussed that this square wave in this particular case consists of many waves, okay, many, let us say, sine or cosine waves. Okay, we have already discussed the Fourier representation. Okay. Now, when you have the dispersion error, so different waves, which means different frequencies, okay, start moving at different speeds. Okay, and that basically depends on the, it starts depending on the wave number. Okay, so if you have a square wave, I mean, if you are just solving this problem del u by del t plus c del u by del x, you expected that all the waves, let us say this square wave or any wave, that any input wave that you have consists of many different waves. So, all those waves will travel at the speed of c, right, that is our expectation. Okay. But what if some waves start moving at a great speed greater than c and some waves start moving at a speed less than c? Okay, and what if they depend on the wave number? So, the representation will be basically, let us say, sin k x, okay, k1 x, k2 x, k3 x. So, there are so many different waves, right. So, what if the speed starts depending on this k? Okay, so that is basically completely numerical. Okay, it is because of your choice of scheme, your different waves are traveling at different speeds. Some are basically becoming greater than your expected speed and some are lower than the expected speed. Okay. So, when the waves are not traveling at the expected speed, that is called dispersion. Okay. So, this phenomena is called dispersion. Okay. And the error due to that is called the dispersion error. Okay. So, this is a very, very dangerous error. Okay. Because if you do not control the dispersion error, what will happen is that your scheme will eventually blow up. Okay. At the same time, so if you use any discretization scheme, it will have error, okay, because you are truncating the Taylor series. Okay. So, it can have the dissipation error or it can have the dispersion error, right. Now, if you want a scheme which is very good for solving a problem, you want to minimize both these errors, right. So, if you have the dispersion error as the leading order term, okay, what will happen is that you will not get unstable solution, you will get some solution, but it will be your amplitude will be basically modified. On the other hand, if you use a equation which has got a dispersion error in the leading order term, your wave number will be basically modified. Okay. So, now our art in CFD is to find out a scheme which has got minimum of these errors, okay, and at the same time you should basically ensure that your dissipation error is slightly or maybe in such a way that it basically mitigates your dispersion error. Okay. So, basically it smears out and it gives you a stable solution. If the dispersion error is in the leading order term, okay, then it is quite possible that your solution will go up. Okay. So, we will have a more systematic discussion on both these errors in the next few classes, and we will understand, like we have used the von Neumann stability analysis and understood the stability, we will do error analysis and find out the errors in different schemes. Okay. We have discussed about the modified PDE, and that will come into picture when we start discussing these errors. Okay. So, with that we will stop today's class and meet in the next class. Thank you very much.